we're going to talk some more today about sequences and maybe move on to series. I don't know if we get that far. The next section is about series. But anyway, sequences is what we're talking about. So last time we were talking about increasing and decreasing sequences. I will just refresh your memory. Increasing means that an is less than an plus 1. That is, it gets bigger every time for every n. And then decreasing means the other way around. Decreasing means that an is greater than an plus 1. That is, the next one is always smaller than the previous one, again for every n. And if you want to demonstrate that a sequence is increasing or decreasing, you got to do some business with inequalities, right? We did, example at the end last time, showing that a sequence is increasing or decreasing. You set up an inequality, and then you demonstrate that that inequality is true by sort of rearranging it, simplifying it until it simplifies down to something which is obviously true. Remember, there's a word for anything which is increasing or decreasing. So if an is increasing or decreasing, then it's called monotone or monotonic. But I think our book says it says monotonic, I believe. These are like synonyms. But I think our book, is that the word I used last time? Monotonic, that's what I wrote on my paper. So, all right. I might sometimes say monotone for a sequence. It means it is either increasing or decreasing. It does the same thing every time. That's why we use the word monotone. It either gets bigger every time or it gets smaller every time. All right? Okay, actually, to demonstrate that a sequence is not increasing or not decreasing is much easier. So to show it's not increasing or not decreasing is easier. To show it is increasing, you have to demonstrate the inequality holds for every n. But to show it's not increasing, all you would have to do is find one particular place where it gets smaller, right, from one term to the next. Increasing means it gets bigger every time. If you want to show it's not increasing, all you have to do is demonstrate one specific time when it does not get bigger. So to show it's not increasing or not decreasing is easier. We can just demonstrate a pair of consecutive terms which either does not increase or does not decrease, depending on which one we're trying to do. Which does not increase. All you have to do is demonstrate a specific pair of consecutive terms. You don't have to deal with like n in general as a variable. You can just plug in specific numbers, which does not increase, I will say, or decrease if you're trying to show that it's not decreasing. All right, so for example, something like, I don't know, 3 over 5 plus n. This is, actually this one is decreasing, but let's demonstrate that it is not increasing. This is much easier to show than to show that it's decreasing. How can we show it's not increasing? Let's just write a few terms here. Some terms, like specific terms, I'm just going to plug in values of n. I get 1 over 5 plus 1. Not 1, 3 on top, sorry. 3 over 5 plus 1 is the first term. 3 over 5 plus 2 is the second term. 3 over 5 plus 3, etc., right? If I were to compute these, this is 3 over 6, which is a half. This is 3 over 7, which is 3 over 7, I guess. This is 3 over 8, etc. And we can see that if we just look at the first two terms, it decreases when you go from 3/6 to 3/7, right? This of course is A1, this is A2. And I'll just say we can see that A1 is greater than A2. right? A1 is a half. A2 is 3/7, which is a little bit less than a half, because a half of 7 is 3.5, right? So A1 is bigger than A2, so the sequence AN is not increasing. That doesn't necessarily mean that it's decreasing. I'm just saying it's not increasing. Increasing, the word increasing means it increases every time. And if you want to show it's not increasing every time, all you have to do is find one specific time when it does not increase, like this. All right. So showing that something is not increasing is much easier than showing it is increasing, which involves working the inequality like we did at the end last time. All right. Let's look at another example. How about AN equals minus n to the power n? And let's try to show that this is not monotonic. All right, remember monotonic means increasing or decreasing. So we have to show that it's not increasing and also it's not decreasing. That's what you have to do to show something is not monotonic. So we'll show it's not increasing and also not decreasing, right? Monotonic means increasing or decreasing. If you want to say it's not monotonic, you've got to say it's not increasing, and it's also not decreasing. All right, I'm going to do the same thing, though. Let's just write out a few terms and see if we can find one where it doesn't increase and find another one where it doesn't decrease. That's the idea here. So let's write some terms. We're starting at 1, so the first one is minus 1 to the 1. Then I get minus 2 to the 2, minus 3 to the 3, minus 4 to the 4. I don't know how many I'm going to have to write out, but remember the goal is I'm trying to look here and find one which does not increase from one to the next, and another one which does not decrease from one to the next. Hopefully you don't have to look too far down the list. Simplify these guys. Minus 1 to the 1 is minus 1. Minus 2 to the 2 is 4. Minus 3 to the 3, 3 to the 3 is 27. It's going to end up being negative because that's an odd power, so this is negative 27. And then 4 to the 4, I don't know what that is. I was not prepared to do this. On my paper I wrote 16, which is definitely not true. I don't know, what was I thinking? 4 to the 4 is 4 times 4. It's 16 times 16, whatever that is. It's positive, though. Positive, can I just say really big? 16 times 16, whatever that is. 256? All right, thank you. I don't have to say really big. 256. Okay. The next number will be a negative number and really, really big, right? 5 to the power 5. But it'll be negative. Okay, can we find pairs of terms here which will demonstrate that it is not increasing, and another pair which will demonstrate that it is not decreasing? Well, I can see two numbers where from one to the next it is not increasing. I think that would be just from the first to the next here. This is not, well, no, that's the opposite of what I just said. This is not decreasing, right? In fact, for those two, it is increasing. But it's not decreasing. So for those two, I would say since, whoa, right. Come on now. Since A1 is less than A2, it is not decreasing, right? Decreasing means it gets smaller every time, but that is a particular example where it got bigger. In that one step, it got bigger. So that means the sequence overall is not a decreasing sequence. And to demonstrate that it's also not increasing, I can just look at the next two, from 4 to negative 27. The value went way down. That means that the sequence overall is not increasing. So I'm going to say since A2 is greater than A3, it is not increasing. All right, and that means it's not increasing or decreasing, so it's not monotonic. That's my goal from the beginning. All right, Any questions about that? This is, I don't know, maybe a little confusing, but it's easier, like algebraically speaking. You don't have to do a whole lot of algebra to demonstrate something is not increasing or not decreasing. All right? Great. One last concept for this section. This is kind of a long section of the book. I want to talk about a sequence being bounded. This is an important concept. Bounded sequences. This is like being a bounded function. I don't know if you talked about bounded functions in your calculus class. A bounded function is one where, like for instance, that function is bounded from above because it's possible to like choose some big number here, I'll call big M, where the M is bigger than all the values of those functions. In that case, you say the function is bounded above by M. And we're going to make the same kind of definition here. Really, that concept translates easily, like directly over to sequences. So here I'm going to write my definition. We say that a sequence AN is bounded above if there is some real number, which I'll write as a big M, and you imagine the big M is like a really big number, although it might not have to be a really big number, but if there is some big M such that the sequence is always less than the big M, all right? If that's true, I should say for every N. If that's true, then we say the sequence is bounded above by M, right? M is called the upper bound. Maybe I shouldn't use the word the. I mean, there are, if there is an upper bound, then there's automatically many upper bounds. You could always choose larger values, and those would also be upper bounds. So M is a upper bound for AN, the sequence. All right? This is just the terminology. It's also possible to be bounded from below. That means there's a number that's like beneath all the terms of the sequence. Now, on this picture here, this function here that I drew is bounded above, but is not bounded below because I intend for you to interpret that this line just continues going down forever, right? And if that's the case, then that function is not bounded below, but it is bounded above. Same idea for sequences, so I'm just going to write similar stuff here. AN is bounded below if there is, I'm going to say all the same stuff. It's just swapping the inequality sign around. Now, in our book, they use big M for the upper bound and a little m for the lower bound. Isn't that cute? The little m is something which is less than everything in the sequence. So if there's some little m such that AN is greater than little m for every n. And we call that number, m is a lower bound for my sequence AN. All right. Simple terminology, bounded above and bounded below. For example, let's just talk about some simple examples. How about AN equals 3 to the power n, all right? The terms, of course, would say 3, 9, 27, 81, and then whatever the next power, the powers of 3, right? I ask you, is it bounded above and is it bounded below? AN is bounded, actually one of them it is. And we want to fill in the blank. Is bounded. Yeah, it is bounded below. That's because there is some number that's less than all of those numbers in the list. What number did you have in mind? 1, sure. Actually, you could have said 0, or even 2, or even, 2.99, which is a strange answer, but it would work. Any number which is less than all the numbers in that sequence would work. Yeah.
I was going with, because if n is 0, then theoretically the lowest number you could have would be 1. So you have to go below that.
Yeah, so if I had started the values at n equals 0, then this sequence would begin with 1 instead, right? In that case, you should have chose a value like 0 or something. So technically, according to the definition, it must be less than, not less than or equal here. Right. But anyway, yeah. So,
Would it have to be like 0.9?
well, I would just say 0. I mean, it doesn't have to be like the best possible bound. It's just any lower bound. So,
So it's not as specific as like the answer to a function or something. It doesn't really matter as long as it's actually below.
yeah, right. So I'm going to say an is bounded below by 2. But there are actually infinitely many different correct values you could put here. Not anything would work. Like, it's not bounded below by 5 because they're not all less than 5. I mean, they're not all greater than 5. But they are all greater than 2. Let me just say, right here, you could have said or 1 or, negative 200 if you wanted to. All you have to do, you just have to choose a number which is less than all the terms in the sequence. There are many possibilities for this answer. All right. AN is not bounded above. That's because this sequence, those numbers continue to get bigger every time, and there is no number which is bigger than all of them, right? Really, this is because the lim of AN as n goes to infinity equals infinity. So it can't be bounded because these numbers continue to increase without bound forever. All right, how about AN equals negative 1 to the power n? My favorite slightly weird example. What would you say about this? Its boundedness? Is it bounded above? Is it bounded below? Or neither or both? I would say both. This is bounded above and also bounded below. You have to ask yourself, can I choose a number which is bigger than all these? Yeah. And can I choose a number which is smaller than all these? Yeah, you can. So this is, AN is bounded above and below. It's bounded above by, say, 2. And it is also bounded below by maybe negative 2, right? You just have to choose any numbers that are bigger than all of those and any numbers that are lesser than all of those. All right? Great. How about, here's maybe more interesting one. N over n squared plus 1. Now we'll have to think a little bit harder about this, perhaps. Is it bounded above? Is it bounded below? Now, to get yourself sort of an idea, it's always a good idea to write down a few terms just to get a feel for what this thing is doing. So if I were to write the terms, the first is 1 over 1 plus 1. The next would be 2 over 2 squared plus 1. 3 over 3 squared plus 1, etc. This is a half. This is 2/5. This is 3/10. So just for the purposes of comparing these numbers, that's 0.5. 2/5 is 0.4. 3/10 is 0.3. Isn't it? Anybody have any feelings about this? Is it bounded above? Is it bounded below? Now, looking at these so far, it seems that they are bounded above. Like, they seem to be getting smaller every time. I don't know about below. What do you think? Yeah. Are you sure it's approaching 0? Like, it's getting smaller. I mean, if it continues, like, if you think that is a pattern, looks to me like it should go next 0.2, 0.1, then 0, then negative 0.1. You don't think that's...
Yeah.
I mean, it's hard to tell at this point, right?
No, I mean, you have to keep doing that. The way that the book had it, they would do the series or sequences of 5, and that way you get a good sense of what the pattern starts
Okay.
with.
Yeah, I mean, we could jump down to the 10th one and see what happens there. That's a good idea. I chose 10 because I prefer to work with 10s rather than 5s, but this is 10 over 101. I actually don't know what that is as a decimal, but it's close to 0.01, right? Okay, so my original suggestion about this pattern was not correct, right? This is a misleading first 3 terms here. This is close to 0.01. Anybody else believe that these are bounded below by 0? Yeah, you're right. 0.1, not 0.01. Thanks.
I would still say that it's decreased. Either way, it doesn't matter if that value is 0.01 or 0.1. I would say it's decreasing from 0 and down to that 0, because if there's a number on top of the number actually being 0.
Yeah, so I think what he's suggesting is this thing is always greater than 0. It's never negative, right? Actually, when you say it that way, can anyone, just by looking at the formula, can you explain to me why this thing is never negative?
Because A, you can't have any negative numbers to represent N in a negative sequence. And C, the number on top is always greater, or the number on top is smaller than the number on the bottom.
Yeah, so these are actually 2 different important facts. So first of all, n over n squared plus 1. Just by looking at this, you can tell this must be positive, right? Say what you will about that, but n itself is positive, and then the denominator is also positive, right? N squared plus 1. So this must be positive. And so that means, you know, an is greater than 0 for all n. And so that means it's bounded below by 0, right? This actually, once you get it in your head that 0 is a lower bound, it's usually not very hard to explain why, right? In this case, it's just because you can tell by looking at it, this thing must be positive. So an is bounded below by 0. Now, he said something else interesting, and that was that in this fraction, n over n squared plus 1, the numerator is always less than the denominator. And I agree with this. Maybe somebody else could tell us denominator. What does that have to do with anything? It actually does have to do with something. The numerator is always less than the denominator. What can that tell you? Somebody else. You've given us so much already this morning. Yeah. More than the rest of us, I guess. What do you think? Yeah, it means this fraction is always less than 1, right? The numerator is always less than the denominator in this fraction, which means that this fraction is less than 1. So an is less than 1, which means it is bounded above by 1. So this is an example where you have to do a little digging and a little thinking about this. But so an is less than 1. So just in the language that we've been using, an is bounded above by 1. You got to just kind of do a little journey of reflection and exploration. That's what mathematics is all about. Every so often I talk to somebody, I meet somebody, tell them I'm a mathematician. Often they say, oh, I hate that, which is like, oh, all right. But often they say, well, I like math. I like math because it's always like cut and dry. You do the thing, you get the answer. And that's really satisfying. And you know, I don't want to diminish, I don't want to steal your joy if you feel that way. But in my opinion, mathematics is much more about sort of exploration. You got to play around with it until you figure something out. It's not in sort of the real life mathematics is not really about just plugging things into formulas all the time. Although that is kind of what like doing your math homework usually does boil down to that, unfortunately. But it's not really the true spirit of mathematics in the wild. Is really about sort of exploring and figuring things out.
Wouldn't you say it's exploration towards a single answer though? Because usually there's a answer or one answer, or multiple of series or sequence of answers.
Yeah, I guess.
Only one set.
I would say it's about like discovering truth.
Oh, that's a good one.
Mm-hmm.
That's now philosophy.
Yeah. And you know, I think most mathematicians actually will sort of take a philosophical point of view that like I do believe in the existence of certain absolute truths, because as far as I can tell, mathematics is absolutely true. I mean, we can make errors and come up with things that we think are true but aren't actually true, but the truths which are deduced mathematically are universal. They're not culturally influenced. Their cultural influences on what we decide to talk about, but not in the facts themselves. This is my opinion, but I think most mathematicians are of this opinion.
I would agree with that. Numbers don't have personality.
Yeah, I mean, right. 2 plus 2 is 4. As long as what we're talking about, as long as we're clear about what 2 means and what 4 means and what plus and equal means, it's kind of objectively true, in my opinion. This point of view. I don't know if you guys really care about this. This point of view is off-putting to some people, though, and so I don't want to emphasize this too much. This is actually I've been reading lately. A bunch of people are trying to have some big ideas about making mathematics less racist, anti-racist mathematics. Um, and this is something that the natural knee-jerk reaction, and to be honest, my knee-jerk reaction is, well, mathematics isn't racist because I can say 2 plus 2 equals 4, and that has no moral content as a statement. It's just a statement about some kind of abstract truth, but it's not. There's no cultural or moral or value judgments at all in that statement, in a mathematical statement like that. And I do believe that. But I think there are cultural ways that we talk about mathematics. For example, if everything you say about mathematics is talking about specific problems which have specific answers and you just have to work at it until you get it right, and you can't get it wrong, because if you get it wrong, you're wrong. You got to get it right. Like that basic framework of discussing mathematics, that is expressing a cultural value framework, right? Which, I mean, I think what I just said, I don't think it's racist, but at least it is reflective of my culture in a certain way. And, you know,
I guess your process somewhat reflects how you learned it, but at the same time, like, how does that even translate to racism? The absolute blow that out of proportion. To me, it seems to argue over something.
yeah, I think there is some of that. I would say so. One thing that I've read, which seems to make some kind of sense to me, is just that for me in my culture, this kind of quest for absolute truth as being expressed in like equations which always have a right answer as opposed to a wrong answer, and the idea that if you got the wrong answer, then you just like wasted 5 minutes of your life, rather than if you got the right answer, you did it right, you did a good thing. I have read that, and I'm not an expert in cultural whatever, but there are people with different cultural backgrounds will hear this expression of my culture and their response will be like, I'm not into that, just because of the way that I said it, not because of what I'm talking about. Um,
That's their racist reaction in a sense. They're just being
well, I wouldn't say they're being racist, but they are comfortable with their universe of cultural ideas, and when I present mine, it's off-putting, or they don't connect with that as easily. I think the idea is when I say stuff like that, other people from my own culture can receive these ideas and learn comfortably, whereas other people from a different culture, maybe this would present barriers to them. Um,
I think learning is cultural differentiation, like the way that people learn things in different cultures. And like
yeah, right.
there's a necessity for that. Like if everybody was the same in the world, like if all countries was the same as Australia, which is the same as China, like there'd be no diversity in the world, there'd be no differences, no limitation, nothing like that.
Mm-hmm.
So because differences are important, people just try to smooth them over.
Yeah, I would say it is my, so this is really more about education. I would say it's my responsibility as an educator to try to present things in a way which everyone in the classroom can understand, like equally. And if there are things, if for instance, I mean, I don't think that this is like an extreme, totally extreme version of the reality, but if, for instance, the way I explain things makes a lot of sense to white people but doesn't make sense to black people, it's not because I have like racism in my heart or something, but I'm producing an environment which has racist outcomes, and so, I mean, I don't think that's
But then, but on the same token, you could say that those, and this is again like an extreme example, but you could say that people are not able to understand the material that's being presented to them. They're not in the right setting.
no. I mean, yeah, but then what I'm saying effectively in that scenario would be my class is for white people and black people should learn from somebody else,
Well, not
which is
necessarily. You're saying that this material is being taught in this specific way, and like to learn it in this way, you have to alter your learning style,
yeah,
your learning, and that's the nature of going to any classroom. I come in here and I learn this way, and then I go to Professor Martin's classroom and he has a totally different teaching style. It's about adapting the
right.
teaching styles, and if you're asking for that then it's the issue with you and not with the professor.
I would say if it's about race, then I mean it's like if I had a blind student in class, I got to change the way that I teach. You know,
100%. You have to present the material that they can understand. But if it's in English
right?
and the class is in an English-speaking country, then theoretically everyone should be able to understand that.
Nah, I think I disagree. But anyway, nothing that you see on the screen right now is racist, as far as I can tell. These things, I take it all with a grain of salt, but I do take it seriously also. Um, to be honest, my students at Fairfield tend to have the same culture as me. They tend to be, white folks from New England, which I am, who don't really think about the cultural baggage of mathematics education. Um, but on some level, it's something I like to think about.
It's an interesting theory too, to look at for sure.
Mm-hmm. All right, let's discuss. Okay, I want to just talk about boundedness as it relates to convergence. All right, so two like big ideas here, and then we'll talk about series. Although I don't know if we'll get there. Boundedness and convergence. I want to ask ourselves questions like, if the sequence is bounded, does that mean that it converges? Or if the sequence converges, does that mean that it's bounded? That kind of thing is what I would like to talk about. There's some kind of relationship between whether or not it converges versus whether or not it's bounded. So let's talk about if the sequence AN converges, then what? Well, if I were to try and sort of graph the sequence terms, converges means like maybe they'll bounce around for a while, but eventually they will all sort of approach the same value. I'm running out of space here, right? this is the picture you should have in your mind of a sequence which converges, right? You don't know for sure what happens towards the beginning of the sequence, but eventually the sequence approaches some particular limit value, which I could say is, that was supposed to be a straight line up there. I'm trying to just indicate where they converge to, all right? Any thoughts about this? Is such a sequence going to be bounded? Or is it possible that the sequence could be unbounded? Remember, unbounded would mean like it goes up forever, or perhaps it goes down forever. I think actually it couldn't go up forever if it's going to converge to a particular value, right? And it also couldn't go down forever if it's going to converge to a particular value. You might wonder, could it have, maybe it's going to converge over here, but maybe it's not bounded over here? Like before it gets to the limit, maybe it goes up to infinity, and then somehow comes back and then converges at the end. That also is impossible. It's because before it gets to the end, there's only like finitely many terms over here, right? So you could say sort of around here, it gets, I'm going to say all subsequent terms are close to the limit number, you know, whatever this sequence is approaching, what it's converging to. And what about all the previous ones? Well, there's only finitely many of the previous ones, right? Like here, I don't know how many there are right here, but maybe there's 10 of those, right? So one of them is the biggest. So it can't just go up forever, because in order to go up forever, that would require at least, you know, a sequence of infinitely many points which go up forever. But when you're only talking about finitely many points, this has only finitely many points. And so it must have just like one which is the biggest in the box and one which is the smallest in the box. And those, that means the part in the box is also bounded, right? So the part towards the end is bounded because they are getting close to a specific value. The part towards the beginning is bounded because there's only finitely many of these. So my conclusion, I don't want to write a proof of this, but this is the idea of the proof, if I were to write the proof, would be based on what I just said. Towards the end, they all get close to a specific number, so it is bounded on the end. And on the beginning, there's only finitely many, so it is bounded on the beginning also. And when I say bounded, I mean they got to be bounded above and also bounded below. So I'm going to write this as a theorem. It says if the sequence AN converges, then AN is bounded above automatically and below. Right? It's not always easy to tell what the upper bound and the lower bound would be, but you know that it has to be bounded above and below if it converges. All right? How about the other way around? What if it is bounded? Does that mean that it converges? Not necessarily. Can you give me an example? Yeah, okay, so let's talk about something which is bounded above and below. Yeah, how about the alternating sequence? 1 minus 1, 1 minus 1, that one? That is bounded above and below, but it doesn't converge. So if AN is bounded above and below, here's the question I was asking. Must it converge? The answer is no. That's because this one, AN equal minus 1 to the n, is bounded above and below. But doesn't converge, right? It is bounded above and below, but it doesn't converge. Another example like that would be something like AN equals cosine of n. This is a very strange sequence. because its values, I can't really say what any of those values are. I could with a calculator, but the first value would be cosine of 1, like 1 radian, whatever that is. That's not an ordinary value. And then cosine of 2 radians, and then cosine of 3 radians. What you would get is just sort of, essentially random points. But they would be bounded. How do you know they'd be bounded? Because the cosine, its answers are always between 0 and 1. So whatever those random points are, this will be bounded. This is bounded, but it doesn't converge to anything. Cosine of n, when you use larger and larger values of n, it doesn't approach something. It just continues to give you this random values between 0 and 1. So this is bounded, but doesn't converge. All right. It turns out there is a theorem about bounded things which converge, and we have enough time to explain. Again, I'm not going to talk about the proof of this, but you will do the proof of this when you take your real analysis class, which is about all of these things. This is called, I'll tell you the name of it, it's called the monotone convergence theorem. And the theorem says if an is bounded above and below, and is monotone, monotonic, then an converges. All right. These two examples that I just did, they were bounded above and below, but they were not monotone, monotonic, right? Remember, that means either increasing or decreasing. So this one here, -1 to the n, doesn't always increase or always decrease. It bounces back and forth between two values. And this one also, cosine of n, is not increasing or decreasing. So these ones were both bounded but not monotonic. It turns out if it is bounded above and below and it is monotonic, it must converge. And I'm going to just try to draw a picture to convince you of this fact. So a sequence which is bounded above and below, that means whatever I draw, I'm going to try and plot the terms here. Whatever I draw, it has this sort of upper bound and the lower bound also. All right? So my terms that I'm going to plot here, the dots have to be between those two numbers, right? And I also have to draw something, so that expresses the fact that it's bounded above and below. My sequence has to stay between these two horizontal dotted lines, and also monotonic. So let's imagine, that means increasing or decreasing. I'm just going to pick one. Let's try and draw points which are increasing. Although you'll see the same will happen if I do decreasing, but I have to pick one for my picture here. All right, I have to make it increase every time. So maybe I start here, and I go here. It has to move up every time as I go to the right. I'm here to tell you, folks, this has to converge, right? Because it has to go up every time, and it can never exceed that big M. That means it must, at some point, stabilize, right? You can't go back down. This must converge. This, what I drew here was increasing. Of course, you can try to draw a decreasing sequence. Again, if the decreasing sequence has to be stuck between those two bounds, it must converge to something if it's going to decrease every time. This is called the monotone convergence theorem. Maybe I'll ask, on my picture, it looks like those points are converging to M. Can you just say, then AN converges? Like, could I add a little thing here? Something like, if it's increasing, it converges to the big M. If it's decreasing, it converges to the little m. What do you think about that? Right, you definitely cannot touch the m, and you certainly can't exceed the m. Although, Yeah, actually, it doesn't have to go all the way to the m, right? For example, I could have drawn, I'll do these in, oops. Um, I could have done, I'll make some blue points here. Come on. How about this? Right? That one also converges, but not to m, right? I mean, it doesn't have to go all the way up to the top. It could go anywhere in between those two bounds. It could converge to, all right? So I will just put a note. It doesn't have to converge to the big M or the little m, all right? But must converge to some value in between. Or equal to. Right? It could approach the big M and converge to the big M. Even if m was an upper bound, so each point individually cannot equal m, but they can still approach and converge to m. But it doesn't have to. Any value in between the two bounds. All right, that's called the monotone convergence theorem. It's a big deal in real analysis. We're not really going to do much with this, but I hope it makes sense from the pictures. All right. Next, we're going to talk about series. I think maybe we'll just leave it there for today, and we'll talk about series next time. We will, as always, start with our quiz next time. See you then.
Thank you.
Bye-bye.